Hello everyone, today we are going to talk about the glass, its role in optic and imaging. First of all, what is a glass? Glass, known as non-crystalline solid with a glass transition, that it is different from crystal that have a well-defined melting point and long-range atomic periodicity. Excellent uniformity and transparency can be achieved by preparing glass in a wide range of styles and shapes, including powder, thin films, and fibers. Unlike crystal, the glass's composition can be adjusted to provide a variety of qualities that satisfy the requirement of particular application. Consequently, glasses have played a crucial role in many of humanity's technological and social development. Next, I will explain about the role of glass in optic and imaging from two different perspectives, which is material science and real-world application. From a material science point of view, glass is very important because its refractive index. When light enters glass, it bends, and this bending allows lens to focus light properly. Another key property is dispersion and wavelength control. Different types of glass handle light differently. For example, crown glass has low dispersion while flint glass has high dispersion. This helps scientists design lenses that reduce color distortion. Surface quality and processing also play a major role. Polishing glass at the nanometer scale reduces light scattering, and special coating improves light transmission, making image more clear. In terms of real-world application, glass allows precise control of light. This is essential for forming accurate image in optical devices. For example, eyeglass use special design glass lens to correct vision problems such as myopia and hyperopia. Glass also has a high optical transparency, meaning it allows maximum light transmission. This produces high-resolution images, which is why glass is widely used in microscope to show clear and magnified image. Next, I will talk about history background. First is the early development of glass from around 2600 BC to the Middle Age. The earliest glass were made from natural obsidian. Later, human-made glass was produced in Mesopotamia using silica, soda, and lime. However, during this time, the glass was mainly decorative and had limited optical qualities, so true optical applications were not fully developed. Next is the foundation of optical glass science from 7th to 19th century. Next is the foundation of optical glass science from the 7th to 19th century. During this period, glass composition improved significantly. Crown and flint glass were developed, providing better transparency and refractive control. Scientists such as Galileo and Fraunhofer contribute to the development of lenses for telescope and microscope. The third stage is industrial optical glass and composition control from the late 19th to the mid-20th century. There was strong collaboration between scientists and manufacturers. Important figures like Carl Zeiss, Ernst Abbe, and Otto Scott helped produce high-purity optical glass. New glass families such as borosilicate, lead-based, and lanthanum-doped glass were introduced. Finally, in the modern optical era, from the mid-20th century to the present, new materials such as chalcogenide, fluoride, oxyfluoride, and glass ceramic were developed. Next, I will talk about history background. First is the early development of glass from around 2600 BC to the Middle Age. The earliest glass were made from natural obsidian. Later, human-made glass was produced in Mesopotamia using silica, soda, and lime. However, during this time, the glass was mainly decorative and had limited optical qualities, so true optical applications were not fully developed. Next is the foundation of optical glass science from 7th to 19th century. Next is the foundation of optical glass science from the 7th to 19th century. During this period, glass composition improved significantly. Crown and flint glass were developed, providing better transparency and refractive control. Scientists such as Galileo and Fraunhofer contribute to the development of lenses for telescope and microscope. The third stage is industrial optical glass and composition control from the late 19th to the mid-20th century. There was strong collaboration between scientists and manufacturers. Important figures like Carl Zeiss, Ernst Abbe, and Otto Scott helped produce high-purity optical glass. New glass families such as borosilicate, lead-based, and lanthanum-doped glass were introduced. Finally, in the modern optical era, from the mid-20th century to the present, new materials such as chalcogenide, fluoride, oxyfluoride, and glass ceramic were developed.
Now I will move on to example of glass application in optics and imaging. One common application is in camera lenses such as smartphone camera and CCTV system. Optical glass help ensure sharp and accurate images. In the medical field, glass is used in medical imaging devices such as endoscope to transmit light inside the human body. Glass is also used in telescope and microscope, where high quality of optical glass allow high magnification and provide image clarity. Next, I will discuss advances and innovation in optical glass. First, low dispersion, which improve image accuracy and also color quality. Anti-reflective glass are also applied to camera lenses to reduce and minimize glare and light reflection. In addition, ultra-thin glass is also used in compact devices such as smartphone, making it lighter and more efficient. Advanced optical fiber technology has also improved high-resolution imaging and data transmission. Moving on to the benefits and advantages of glass in optical systems. Glass is widely used in medical, photography, and scientific instrumentation industries because of its excellent optical properties. One major advantage of glass is its high optical clarity, which produces sharper and more accurate images. Glass also has high thermal stability and is resistant to deformation, means that it can maintain its shape and optical performance when exposed to heat. Because of these properties, glass is suitable for long-term use. Now, I will be discussing the challenges and limitation of optical glass. First, it's brittle and prone to cracking under mechanical stress, which is limit the durability in drug application. Second, the high cost of manufacturing and processing high-purity optical glass can be prohibitive, especially for large-scale or consumer products. Third, it has limited flexibility. Unlike polymer or composites, glass cannot bend without breaking, which restrict design possibilities. And finally, light reflection at glass surfaces can cause glare and reduces image contrast, often requiring anti-reflective coatings to mitigate.
Now, I'll talk about the future trend of glass. First, building integrated photovoltaics or BIPV. It is a glass-based technology that allows windows and facade panels to produce solar energy. The panels can be transparent or opaque and are integrated directly into the building, turning normally inactive elements into energy producers. This technology is still new and is expected to become more advanced and widely used in the future. Next, the optical MEMS mirrors. The optical MEMS mirrors is actually a rising demand in automotive systems, AR or VR, and optical communications. These tiny mirrors are becoming smaller, cheaper, and more precise, allowing them to be used in advanced sensing, imaging, and smart devices. Although MEMS mirror technology is already being used today, it is still developing, and we expect even more advanced applications and improvements in performance, efficiency, and new industries in the future. In the conclusion of this presentation, glass is a vital material in optics and imaging due to its high transparency, control refractive index, and ability to precisely manipulate light. Over time, improvements in glass composition and manufacturing have enabled its use in cameras, microscope, medical imaging devices, and advanced optical systems. Although optical glass faces limitations such as brittleness, refraction losses, and high production costs, its benefits in image clarity, durability, and performance outweigh these challenges. With ongoing innovations like building integrated photovoltaics and optical MEMS mirrors, glass continues to play an essential role in modern and future optical technologies. That is all from us. Thank you.